So this process here of radioactivity describes the phenomena of natural radioactive decay. This idea of natural meaning that this is happening spontaneously. This is not an action of people or man or instruments. This is happening naturally. Some particles are not stable as they are. And we're going to look at different types of particles that are like that. Some nuclei are not stable, and over a period of time they're actually breaking down by themselves. It's a natural process. Radioactive decay, in other words, they're giving out something. It can be a particle. It can also just be pure energy. They're giving out energy to become more stable. So basically everything in life, the natural law of life, your idea of entropy is wanting to be more stable, heading to more stable states. So this process of radioactive decay is looking at nuclei becoming more stable. More stable, and they do this by giving off some, usually a particle. They give off, as we're going to see, they either give alpha particle or beta particle, or sometimes just pure energy in the form of radiation. This gamma particle, as we're going to see, is a high energy wave. It's giving off energy, so gives off the energy, and they are more stable. There's less energy in the nucleus. Okay, so let's start off with alpha decay. We've got some polonium here. It's got an atomic mass number of 211. Lead, and what happens that over a period of time it actually breaks down. This polonium 211 is not stable. Alright, so it's actually very unstable. As we're going to see here, its half-life is about half a second. So that means in half a second it has lost half of the nuclei have actually changed into lead. So if I add some, let's add some here. Alright, so I'm adding some here, and they are changing. These are changing from polonium. So if I stop this now, we've just gone just over the half. Well, we actually haven't reached. Let's go to the half-life. Let's continue to the half-life, about over there. Now, at the half-life, out of the total number in the beginning, roughly half would have changed into lead over that time. So it's like half a second. Now, obviously, there's time delay here. This is going a little bit slow. This wasn't half a second, obviously. Gives us a bit of a time to think about it. But if I counter these over here, you should be getting. So say if I had 100, if I put in originally 100 polonium nuclei here, at the half-life, I would expect that I would have about 50. All right, there'll be 50% left of the original number of nuclei. All right. If I continue it for another half-life, say just past 1 over here, continue it, giving off, alright, to just over there, stop it there. Now, if there were 100 polonium to start with, how many would you reckon now going about 2 half-lives? It'll be about 25, alright, so you had 50% there left. Now after another half-life, now the 50% was left, 50% have decayed. So now you're at 25%. So each time it's halving. So another half-life about over there, say, you would expect now there would be about 12.5. All right. Now obviously there wouldn't be, either be 12 or there would be 13. But usually, when you're talking about these things, you're not talking about 1 or 2 or 100 even. You're talking about billions of these things. So you can get a pretty good idea from that. So these things are actually changing. Now, what's actually happening here? Well, we got the polonium, right? So it's I think it's PO, hopefully. Yes, it is PO. There we are. PO, and it is 211. And it goes to not uranium, it goes to lead, PB, and that's 207. And it also gives off an alpha particle. Now, an alpha particle is a helium nucleus. A helium nucleus is made up of a regular helium nucleus is made up of a nucleus with 2 protons and 2 neutrons. So it looks something like this. It's got 2 and 4, and an alpha particle is a helium nucleus where all the electrons have been stripped off it. So it's actually 2 plus there. All right. So it's given off. It's given off that. That's your alpha radiation. Now, does anybody know what the atomic number for lead is? I think it's about 82. Can we just? Would anybody like to just quickly check that up? Just Google that quick. I'm going to go with 82 at the moment. If you find that it's wrong, we'll just quickly adjust those numbers. So it's 80. Is it 82? So what would you reckon that the atomic number of polonium is therefore? What is the atomic number of polonium? There we are. If you can just check your periodic table. Great, thank you. You'd think it would be 84, wouldn't it? Because here you had 82, and here with the alpha particle there are. Sorry. It's 84. 84 is what we'd expect, because you got 82 here. You got 82. You got 2 here, so this should be 84. All right. Your atomic mass number. Your atomic mass number is 211. 207 plus 4. 211. Alright, so you're getting a balancing here of both your number of neutrons and of your number of protons coming out here. Now, by giving off this alpha particle, this comes from the nucleus. This lead nucleus is much more stable. Alright, this is radioactive in that the nucleus is not stable naturally. Okay, it won't remain. So over a period of time, it gives off the alpha particle. It forms a more stable nucleus. Now, if I took the mass of this, and called this M2, and if I took the mass of this and I call this M1, how would those masses relate? Which one should be more? M1 is more. Yeah, loses energy, yeah. That's right. So, yes, so that's on that side when you're actually going and you're making from smaller to bigger. The smaller ones, when you're doing nuclear fusion, as we're going to see later on, we're going to see a graph that actually shows how it works. When you get very small elements and you put them together, they become more stable. But when you get up to iron is the most stable element, and it's the most stable nuclei. It's got the highest bonding. It's the most difficult element to break apart. As soon as you go past iron, it actually becomes less stable. The bonding actually becomes less. So when you get heavier elements and they are getting smaller, they actually become more stable in getting smaller. All right. So your M1 and your M is greater than your M2. If I take M2 minus M1 and I multiply it by C squared, I get the energy that is released. Alright, so that mass difference there is the energy that is actually being released by that reaction. That is fission. That's what happens. It's fission. It's a breaking up of nuclei into smaller nuclei, and there is an energy. There's energy release in that whole process.